Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss thermoelectric effect and application of second law of thermodynamics to thermoelectric effect. Let's begin. Thermoelectric effect. The name indicates thermo means heat, electric means electricity. The phenomenon of producing electricity with the help of heat is called thermoelectricity, and the phenomena is called thermoelectric effect or Seebeck effect. Producing electricity from heat named as thermoelectricity, and this phenomenon is known as thermoelectric effect, or also we can say it as Seebeck effect. So we consider an example. Let we take a thermocouple. Thermocouple means two elements those two elements are thermally related. In this case, we consider the thermocouple of copper and iron. Example of that thermocouple: copper and iron thermocouple means FeCu thermocouple. So the figure of that thermocouple let that point be A, let the point B, this is the darkened portion Fe, single line portion as copper. How the functionings? This portion is hot, that portion is cold. Let one junction that is kept hot and other junction is kept cold, and a galvanometer G is connected in that of thermocouple, that shown in that of figure. Then galvanometer gives deflections as the thermoelectric current is produced inside that of thermocouple, and current flow from copper to ferrum means copper to iron at hot junction. In that of hot junction, copper to iron current flows, and iron to copper at cold junction. The flow of current in that of thermocouple shows that there exists thermo EMF, thermoelectromotive force. That is why the current is produced. That thermo EMF between hot and cold junctions of that of thermocouple is produced. Hence, the production of thermo EMF which causes the flow of thermoelectric current when two junctions of thermocouples are maintained at different temperatures is called that of Seebeck effect. Okay, due to the thermo EMF between hot and cold junctions, thermocurrent is produced. So, we get electricity from that of heat, that is known as thermoelectric effect or Seebeck effect. The best example of Seebeck effect is the maximum amount of EMF, or we can say thermo EMF, is produced for that of antimony and bismuth thermocouple. In that of example, we consider copper and iron thermocouple, but in case of antimony and bismuth thermocouple, it is maximum amount of thermo EMF is produced at a given temperature. Now, here is that Seebeck effect, which is reversible in nature. That Seebeck effect, it is reversible in nature, and let we calculate the coefficient of Seebeck effect. What is that of coefficient of that of Seebeck effect? The rate of change, of thermo EMF, the rate of change of thermo EMF with temperature is called Seebeck effect. Seebeck effect coefficient. So, it is denoted by, therefore, Seebeck coefficient, S is equal to dE by dt, at the rate of change of thermo EMF, where E is the thermo EMF, sorry, that is d by d theta, not t, that is d by d theta, where we take E as thermo EMF, and temperature of hot junction be the theta is the temperature of hot junction. This is the Seebeck effect and Seebeck coefficient. Now, another type of effect, that is Peltier effect. What is Peltier effect? To understand Peltier effect, let we choose copper ferrum thermocouple, or that is copper iron thermocouple. This is thermocouple, that is A, that is B. A is at hot, B is at cold, and the bold portion we say that is iron, and single line portion that is copper. And another figure shows we connect a cell here, a battery, that is a potential differentiator here. That is a that is B. In A, heat is absorbed, here heat absorbed, here at B means in that colder portion heat evolved, heat evolved. So, what happens here? If we say copper ferrum thermocouple and insert a cell in that of thermocouple as that shown in that figure, so that the current flows as in that figure, that is the direction of current flow in the same direction as due to the previous one in case of Seebeck effect. Then heat is absorbed or evolved at a junction that is proportional to the quantity of charge crossing to that of junction, and if A is the hot and the junction B is cold, then heat is absorbed at hot junction and heat is evolved at cold junction. That means the absorption or evolution of heat at a junction of two dissimilar metals, these two are dissimilar metals, when current is passed is known as what? Peltier effect, is known as Peltier effect. And let me calculate the Peltier coefficient. What is that of Peltier coefficient? The amount of energy absorbed or evolved per second at a junction when a unit current is passed through it is known as Peltier coefficient. Peltier coefficient, that is known as Peltier coefficient, and that effect is reversible. It is reversible also, like that of Seebeck effect. And let me take if two junctions of a thermocouple are at temperatures T and T plus dt. Let here is the T temperature, and here here is the T temperature, and here is the T plus dt temperature. T plus dt temperature means temperature difference, and let the thermocouple EMF is E. So, then we say the Peltier coefficient, that is denoted by pi. The Peltier coefficient pi is equal to T into dE by dt. The Peltier coefficient pi is equal to T into dE by dt, that is Peltier coefficient. Peltier coefficient. And in place of dE by dt, we can write dE by dt. Sorry, here as you take dE by d theta, that is not dE by d theta, that is dE by dt here. dE by dt, here T is the temperature of hot junction, and in place of dE by dt, we substitute the S, that is the Peltier, that is the Seebeck coefficient. So, pi Peltier coefficient is T into S. S is the Seebeck coefficient. The relation Peltier coefficient and Seebeck coefficient. Here S stands for Seebeck coefficient. Another effect, that is Thompson's effect. What is Thompson's effect? Here we take a copper wire whose one end is kept hot and other end is kept at cold. So here we take a copper wire, that is a copper wire, one end is at hot and another end is at cold, and let current is flowing through that of copper wire from hot end to cold end. Then heat is evolved along whole of the length of its copper wire. Since the current flow, so heat will be evolved in terms of some energy or heat loss. Due to that of heat loss, look here, heat is evolved or evolution of heat along that of whole of the length of that of wire when current is passes through that of wire, whose one end is at hot and the other end is at cold. That type of effect is known as the Thompson's effect. The absorption or evolution of heat along whole of the length of that of wire when current is passed through that of wire, whose end is kept hot and other end is kept at cold, is known as Thompson's effect. And Thompson's effect is of two types also, like one is positive Thompson's effect and another one is negative Thompson's effect. Positive Thompson's effect, another one is the negative Thompson's effect. Sorry, it is of three types, and final one is the null, or we can say that is the zero Thompson's effect. Next, the Thompson's coefficient. The Thompson's coefficient, Thompson's coefficient, Thompson coefficient, which is denoted by sigma, is the amount of energy absorbed or evolved per second between the 2 points of that of conductor having a unit temperature difference. When a unit current is passed is named as the Thompson's coefficient. So this is the amount of heat energy absorbed or evolved per second between 2 points of a conductor, 2 points of a conductor having a unit temperature difference, having a unit temperature difference when unit current is passed is known as that of Thompson's coefficient. These are the three effects in case of thermoelectric effect. One is Seebeck effect and Seebeck coefficient, another one is Peltier effect and Peltier coefficient, next one is Thompson's effect and Thompson's coefficient. So these are the effects which we find in case of thermoelectric effect. Let us calculate what should be the application of second law of thermodynamics to that of thermoelectric effect. By using these three coefficients we derive a relation. So let us discuss about applications of second law of thermodynamics to the thermoelectric effect. Actually, Seebeck effect is the resultant of Peltier effect and Thompson's effect. Therefore, we can write the total Seebeck effect, total Seebeck effect is the sum of Peltier EMF, that is the Seebeck effect means Seebeck EMF, Seebeck EMF produced in that of Seebeck EMF is the sum of that Peltier EMF plus Thompson EMF. Since Seebeck effect is the resultant of Peltier effect and Thompson's effect. Let me consider a thermocouple. Let me consider a thermocouple consists of two metals. Here is the thermocouple having two metals. Let that metal I show here is the darkened portion, that metal in a single line portion, and that metal be A and that metal be B. These are the metals. A and B are two metals. Here A, B, that stands for two metals, which is Thompson's coefficient in that of case are positive. Okay. Let sigma A is the Thompson's coefficient of metal A, that is the Thompson coefficient of metal A, and sigma B the Thompson coefficient of metal B. And let you take the temperature of cold junction. Here let we take one junction is cold and another junction is hot. So, let temperature of hot junction is T and the temperature of cold junction be T, cold junction be T, and temperature of hot junction some increment in temperature, that is T plus dt. Here is the temperature of cold junction, that is the temperature of hot junction, T plus dt. Due to Seebeck effect, thermoelectric current will flow through that thermocouple, that is the direction flowing of that of thermoelectric current. Let us assume that current I flow from A to B. Let here I take I be the current flow from A to B. Okay. From A to B or B to A. A to B in what portion? A to B in at cold junction and B to A is at hot junctions. Current flow from A to B in cold junction and B to A in hot junction. Okay. let the Peltier coefficient at temperature T, let the Peltier coefficient at temperature T is equal to pi, and Peltier coefficient at temperature what T plus dt is equal to similarly pi plus d pi. Let us apply the idea of Carnot cycle to that of thermocouple. We use that of idea of Carnot cycle. Here idea of Carnot cycle is implemented. Idea of Carnot cycle here is implemented. What happens to that of thermocouple? According to Peltier effect, heat is absorbed at hot junction A and rejected at cold junction B. Here is the A, hot junction A, here is the cold junction B. Hence, end A will act as source at temperature T plus dt, since we apply the concept of Carnot cycle, that remember in mind. So, that A treat as the source which is at the temperature of T plus dt, and the end B will act as sink at the temperature of T. So, here this is act as source, here it act as sink. Again, this happen in case of Peltier effect. Peltier effect, that is source, that is sinks. Due to Thompson effect, what happened? Thompson effect, heat is evolved along that of whole length of metal A, and heat is absorbed along whole of the length of metal B. Heat is evolved at metal A and heat is absorbed at metal B. Hence, metal A will act as a sink at temperature T, and metal B act as a source at temperature. The temperature will be how much? That is T plus something, T plus dt by 2, that is the sum of the temperature, and that temperature is approximately equal to, that means T. So, that length act as sink, this length act as sink, and that length act as source. Remember that here we use the concept of or idea of Carnot cycle. First case we use Peltier coefficient, that point act as source, that point act as sink. Again we use Thompson's effect, that length treat as sink, that length treat as source. What happenings or what are the happenings in case of these two effects? Let we take in a mathematical overview. So, due to Peltier effect, heat absorbed per second from source A at temperature will be how much? T plus dt at temperature T plus dt, temperature T plus dt, and that absorption will be what? That is current into pi plus d pi, current into pi plus d pi. Okay. T plus dt is equal to pi plus d pi. And heat rejected, here is the heat rejected to sink B per second at a temperature T will be how much? That is I times of pi, that is current into that coefficient term. This is due to Peltier effect. So, what happenings due to Thompson's effect? Due to Thompson's effect, heat absorbed per second from source. Source means at metal B. Here is the source is the metal B at a temperature T is equal to I times, that is sigma B into T. Sigma B, we take the Thompson's coefficient of metal B. This is the heat absorbed. Then heat rejected, per second to the sink. Sink means metal A at temperature T. At temperature T is equal to I times sigma A dt, sigma A dt. Now, the EMF, these are the two cases, heat absorbed or heat rejected, due to that of two effects, one is Peltier effect and another one is Thompson's effect. In that overall perspectives, the EMF developed, here the EMF developed in that of thermocouple, is due to both Peltier effect and Thompson's effect, Thompson effect, and that is equal to dE, and the electric energy consumed, then the electric energy consumed per second in that circuit will be I times of dE, I times into dE. According to the law of conservation of energy, what happens? IDE is same as heat absorbed per second minus to that of total heat evolved. So, according to law of conservation of energy, IDE is equal to total heat absorbed per second minus total heat evolved per second. Total heat evolved per second. So, IDE total heat absorbed, here is the total heat absorbed I pi plus d pi and I sigma b t. This is the heat absorbed, these are the heat evolved or rejected. So, total heat absorbed will be how much? That is I pi plus d pi plus I sigma b dt minus I pi plus I sigma a dt. Taking I as common, that is pi plus d pi plus sigma b dt minus pi minus sigma a dt. Here that term cancelled. Pi minus pi cancel out each other. So, here this is I dE or it is I dE is equal to I times this d pi plus sigma b dt minus sigma a dt, or I cancel out. So, dE is equal to, that is d pi plus sigma b dt minus sigma a dt. Here dE is equal to, that is d pi, taking common as dt, so that will be sigma b minus sigma a into dt, taking as a equation number 1. As we know from Carnot cycle, that is Q1 by T1 is equal to Q2 by T2, where Qn is the heat absorbed from that of source at temperature T1 and Q2 is the heat rejected to the sink at temperature T2. Now, apply this equation to thermoelectric effect. Now, apply this equation to thermoelectric effect. So, what happened here? Q1 by T1 means heat absorbed at temperature T1. So, the terms where heat absorbed, let I evaluate these are heat absorbed. Here is the heat absorbed, here is the heat absorbed in that of time T plus dt in the time T. So, I write here that will be I pi plus d pi divided by T plus dt, next plus I sigma b dt by T, next heat released, that is I pi by T plus I sigma A dt by T. These are the heat released at temperature T, heat released at temperature T. So just we use here what? Carnot's cycle to that of thermoelectric effect. Now simplifying that mathematical equation, all these terms pi taking on both sides as common and cancelled with each other, the remaining term pi plus d pi divided by T plus dt plus sigma b dt by T is equal to pi by T plus sigma A dt by T, or that is sigma b dt by T minus sigma A dt by T, that to that side and this to that side, is equal to pi by T minus pi by T plus d pi by dt. Again here sigma b minus sigma A taking as common, so dt by T is equal to here pi dt plus T taking the LCM and multiplying minus T, that is pi plus d pi divided by T whole into T plus dt is equal to, now expand that brackets, pi dt plus pi T minus pi T minus T d pi divided by T plus dt. Next it will be pi d cancel out, here pi dt minus T d pi divided by T whole into T plus dt. Now neglecting dt in the denominator on RHS, so neglecting here we neglecting T plus dt is very nearly equal to that of T, so it will be pi dt minus T d pi divided by T square, T into T, that will be T square. From these sides 1T cancel out, therefore sigma b minus sigma A dt is equal to pi dt minus T d pi divided by T. Next that is pi dt by T minus T cancel out, that is d pi, here is the sigma b minus sigma A dt. Now dividing both sides by dt, what we get, that is sigma b minus sigma A is equal to, that is pi by T minus d pi by dt. Here is the dividing both sides by dt, or d pi by dt, d pi by dt is equal to pi by T minus sigma b minus sigma A, or d pi by dt is equal to sigma A minus sigma B plus pi by t. Here taking as another equation, equation number 2. But we know from equation 1, dE is equal to d pi plus sigma B minus sigma A dt. From equation 1, we get dE is equal to d pi plus sigma B minus sigma A dt. Now here let we dividing both sides by t. It will be dE by dt is equal to d pi by dt plus sigma B minus sigma A. Here we dividing dt on both sides. d by dt is equal to d pi, that much. And from equation 2, it will be d pi by dt is equal to sigma A minus sigma B plus pi by t. So now in place of d pi by dt, we substitute that term. So I write it in a simplified manner. From these two equations, means d pi by dt, that equation 2, and that equation. So here I put the value of d pi by dt, that is sigma A minus sigma B plus pi by t plus sigma B minus sigma A. Here is the from equation number 2. So simplifying that one, that will be pi by t. These two terms are cancelled with each other. That is pi by t is equal to what? dE by dt. Here is the dE by dt is equal to pi by t. Let equation number 3. But from Peltier coefficient, Peltier coefficient, pi is equal to t times of dE by dt. Now differentiating with respect to t, differentiating with respect to t, we get, that is d pi by dt is equal to differentiation of this term treated as constant. So d, second order differentiation of d square e dt square plus d by dt. So here that is t d square e dt square, in place of dE by dt we substitute dE by dt, we substitute the value like this, dE by dt here, dE by dt look at this term here, d by dt, d by dt here, in place of d by dt I substitute pi by t here. What? But in terms of d pi by dt our requirements, so I substitute in place of d by dt that term here, that is what, d pi by dt, our requirements in terms of d pi by dt. So d pi by dt plus sigma b minus sigma a. From these two sides, here is the d pi by dt, d pi by dt cancel out. Here we say that t d square e dt square is equal to sigma a minus sigma b, sigma a minus sigma b. That is the required expression. See the applications of second law of thermodynamics to thermonic effect, thermoelectric effect. So what is the discussions throughout that of video lecture. So with the help of this video lecture we understand what is thermoelectric effect, Seebeck effect, Peltier effect and Thompson's effect, and using these effects we say the application of second law of thermodynamics to the thermoelectric effect. These are the findings, just a simple mathematical procedures, and finally we get an expression for this. So with this useful and informative notes, let me wind up this session. Thank you.